The history of the atom begins more than 2,000 years ago. Starts with the Greek philosophers when the idea of the atom first came up. It was by a man named Democritus. Democritus was the person who said that everything, you, me, the trees, everything, was made up of small, indivisible particles that were just piled together and linked together, kind of like marbles. He named this atomus because the word in Greek means that you cannot divide it or it is whole. But his idea of the atom didn't take off right now because another Greek philosopher kind of squashed the idea. And this philosopher is a little bit more well known. His name is Aristotle. Aristotle basically asked him three questions. Said, really? We're bags of marbles? If we are, then what holds us together? Why can't we see them? And why don't we just fall down like a bag of marbles? Well, Democritus could not answer these. So basically, the idea of the atom went to the wayside, and everybody kept believing that everything in the universe was one continuous piece of matter. This stayed around for centuries. During the Crusades in the Middle Ages, you don't really hear a lot about science. Everything kind of stays the same as far what as what they were thinking. There were the Moors or the Arabs out of Africa that had everything. I mean, they had running water, they had dentistry, reading and writing, um, they had breweries, and they were already doing genetic engineering um, just through growing the plants and picking out the best plants and making sure that those were the seeds that they went on and used. So these very complex gardens that they had were just a few of the things that the Moors had. It's not until we get into the 17 and 1800s that we actually start seeing people beginning to do science again. And this wasn't in companies with labs and equipment. This was just people in their kitchens. They were just taking the ideas that if I do this, then this will happen, and trying different ways. Does this always work? Does it just sometimes? And basically that's where science really begins to come up again. And really it came out of necessity. You need something to make, you know, getting water easier. So running water was developed. Then they needed a way to keep the plants out or the bugs out of the plants. So they then work to invent some type of pesticides that would keep the bugs out and allow the plants a better chance of growing their crops. An example of how science is really kind of trial and error and trying to get to the basis of things is Joseph Priestley. Joseph Priestley is the one who actually prepared pure oxygen. He just didn't know it. What he did was he took mercuric oxide and he broke it down into mercury and oxygen, and he noticed that how bright the flame was when he did this. And so he thought that something was actually being given off or produced from the fire. And he is also the man that invented soda. and laughing gas. So, um, when he was doing his experiment with mercuric oxide, he, as I said, he felt like something was actually being given off that you could capture. And he called this then the perfect air. And what he actually called it is deflagellisticated air or perfect air. And that was because the flame was so bright, he thought that it was being given off from the materials as they were burned. And what he had actually found was that oxygen makes things burn more intensely. You have to have oxygen there to um, for anything to burn. So it's not so much that he got it wrong, it's that he just didn't realize what he had found. But he stuck with his theory that this phlogiston was developed as you burned things all the way up to the very end. After Priestley, then another scientist came along, and what Antoine Lavoisier is known for is working with metals, kind of like Priestley was, and finding out that really it's not this phlogiston that's being given off, that it's actually taking it from the air around it. And our scientist, Antoine Lavoisier, was really, nothing more than a tax collector. It was just, again, his inquiring of wanting to know why something was and working through it that developed the theory that this phlogiston did not exist and it was something that was already present. And that's where we went to discover oxygen. Antoine Lavoisier did live during the French Revolution. He was very close with the nobles, and because of that close linkage with them, he was actually beheaded during the revolution. So Lavoisier made Priestley's theory of the phlogiston or the perfect air um, to be completely wiped out. As I said, Priestley still stuck to the fact that that's exactly what happened and all the way up to the very end. He never quit believing in the work that he did. What Lavoisier did that proved this, as I said, he worked with metals. He would take a piece of metal, he would burn it, and then he would have the mass of it prior to burning it and after burning it. And what he found was that it actually would weigh more after burning it than it would before. So, how could it weigh more if it was giving off this phlogiston, this deflagellistic, air, this perfect air? How could it be giving something off, but it gets heavier? It didn't make sense. So that's really what disproved Priestley's idea of this phlogiston. You're probably familiar with the law that states that matter cannot be created or destroyed in a chemical reaction, simply converted from one form to another. And that is called the law of conservation of mass. And the scientist we credit with that is Lavoisier. He said the reason the mass of the metals went up after they were burned was because of the oxygen in the air, which then bonded with the metal that the flame gave it the ability to do. It gave enough, put enough energy in there that the oxygen could be taken from the air and bonded to the metal he was working with. Joseph Proust came up with what's called the law of definite composition. What he looked at was that every time you have a compound, then the ratio of the elements always came out to be the same. So um, when this kept holding true, that's when he proposed that, well, there must be a definite composition to a compound. So if it's made up of compounds or elements, they're not just simply mixed together. They have to have a recurring um, ratio of parts. Now that we've had some things that have started to come up and we're starting to get an idea about matter and that it is made of smaller particles and things, then um, a school teacher by the name of John Dalton actually took all of this information and put it together in what he calls the atomic theory. Now, he didn't simply just take everybody else's work and put it together. He was working on some things himself, looking at the fact that a a compound had a specific ratio. So, like if I have water, there's always 2 parts hydrogen and 1 part oxygen. That's the ratio for it, is a 2-to-1 ratio. Well, he proposed that there wasn't only one substance that those elements could make. So if you look at, you know, carbon and oxygen, it can produce carbon dioxide, a 1-to-2 ratio. 1 part's carbon to every 2 parts oxygen. But carbon and oxygen can also be brought together and with a ratio of 1-to-1, which we call carbon monoxide. So same 2 elements make 2 completely different compounds. One we exhale every time we breathe, and the other one is deadly and could kill you. It seems pretty obvious to us now. It wasn't as obvious back then because they didn't have the background knowledge that we have. They were starting from scratch, from, hey, what happens when I put 2 things together? And what do I call that? So even though now we're like, okay, yeah, we know there's carbon dioxide and carbon monoxide. Got it. Not a problem. They didn't have that background. They're developing our background through this investigation and this indirect evidence of not being able to see the things, but still working with it and looking at what happens, the effects of it. They're able to discover then what's causing some things to happen. So, as I said, John Dalton then took this work that had been going on before him and the information he had, and he put together then what we now call the atomic theory. One thing had not changed from the time of um, Democritus is that they still believed that atoms were indivisible, indestructible, tiny solid pieces. And they believed that atoms of a given element were identical and atoms of different elements were different. And whenever a compound was made, they were always put together in whole number ratios, which was Proust's law of definite proportions, and that a chemical reaction can not destroy or create matter, it can just simply rearrange it, which was Lavoisier's uh, law of conservation of mass. So nothing has changed. And we went from Democritus's time in like 400 BC all the way up here into the 1800s with John Dalton. So again, almost 2,000 years had passed before they even began to think about what, what Democritus said could possibly be correct. Now we know, since we have more information than John Dalton has, we know that our modern atomic theory doesn't exactly coincide with what he said because we know about subatomic particles and we also know about isotopes, that things can be heavier than other atoms. So if we look at the structure and the part that's responsible for all of these chemical reactions that they were working with, that leads us to see what the first part was that would be discovered, and that is the electron. At this point in time, a lot of experimenting with energy and light, electricity was going on. So, with the electron being part of the atom, um, what do you think was its property that led for it to be the first one discovered? Well, that is because the electron is on the outside of the atom. You've got your outer area that takes up most of the volume and your very dense center that contains most of the mass, but very, very small portion of the volume. And the electrons spin around just like the little Jimmy Neutron symbol. If you think about that, those are the electrons that are spinning around the nucleus of the atom. Electrons can be added or removed from an, sorry, electrons can be added or removed from an atom um, very easily. And that's what caused things to end up being charged. They still didn't have a lot of technology. So what they were working with um, was, natural electricity, like lightning and things like this. So if we think about early 1800s. We think of all of the basic work being done with electricity, then we'll probably have a person come to mind. And hopefully, when you think about electricity, this person jumps right into your mind because he is the person that gave us or coined the terms charged particles, positively charged and negatively charged. And this man was Ben Franklin. So, Franklin had no idea about the atom. They hadn't really discovered any of the parts when he was working. They just knew with his work um, that there were charged particles. So then that's when they started trying to investigate further, saying, well, why is it that when I have oppositely charged particles that they will attract each other? Or if I take two, sometime they'll repel each other. So Ben Franklin then put words to the fact that opposites attract and like charges repel. One advancement that led to the discovery of the electron was what was called Crookes tube, or what we now call the cathode ray tube. And this basically was able took an electric current and ran it through a vacuum tube, and you could see a beam of light that would run through there. Then um, scientists were convinced that this beam was actually made of something. So then that became their next thing that drew them into investigation. So they were looking, what is the cathode ray? What is it made of? A man by the name of J.J. Thomson was able to answer this question. In his testing, he was able to discover that you could cause that beam of light to bend. So if they could physically move it, then Crookes was correct. It was made of something. So by looking at what happened when they used charged plates and put it above and below Crookes' tube, they could see that the beam was attracted to the positive plate. Well, based on what the information they had gained from Ben Franklin, that opposites attract, they had to feel, so they felt if it was bending towards this positively charged plate, then it has to be oppositely charged. So therefore, that ray that's running through the cathode ray tube must be made of negative particles. What J.J. Thomson actually called these were corpuscles because a corpuscle was like a capsule. And that's what he kind of envisioned electrons being, were these little capsules that were charged, so negatively. So that's where he came up with the term corpuscles, and then later on we come up with the term electrons. So the movement of these electrons is what we know as electricity. So you can see that if you take a magnet will also cause the cathode ray to bend towards the positive end. What we know today that started off as the cathode ray tube was the television, beginning with first the black and white television and then the color television. The black and white had one beam, and so it gave light in some places and then shadowed in others. And then now we have our colored TV. So they used to call the television like the boob tube, or, get out and get away from the tube, whatever. And that was all because that's what operated it. What made it possible was this cathode ray tube that was in there that moved the light, and then as it passed through a charged field, it would cause it to bend into the correct location and show up on the screen that would give you then your light versus dark and give you your image. Robert Millikan is the person that actually came up with what the exact charge and mass of an electron was. He used two charged plates, and as he sprayed oil into it, then he was able to allow these electrons to stick to the oil, and then he could get them to hover. And knowing the information about the oil, he was able to determine how much of that was then this particle we called the electron. What we refer to as this electron that attached itself to the oil, what we refer to that as is static electricity. This is just another look at how the experiment was set up, where you can see how the radiation was coming in and the oil was going in between the plates, then um, how they could be gaining, the oil droplets could be gaining the electrons to be suspended to determine their mass. Now, they knew atoms were neutral, and that everything didn't repel or attract. So then it went to stand that if there are these negative particles, what's going to balance out a negative? Well, a positive. So Goldstein used Crookes tube, but what he did was he moved where the electric current was coming in. He moved it more towards the center, so then it had the option of moving towards the positive plate or moving away from the positive plate. And he discovered when you moved that, then you not only got your green cathode ray tube, you also got a purple cathode ray tube that was made of what we now call the proton. So electrons went towards the positive, away from the positive, meant they were repelling, so it must have been a like charge, so that's how they get their positive particle. Then all of this information was taken and put together by none other than J.J. Thomson. What he put together was a model of the atom, of what he thought it looked like. And a popular dessert at this time was known as plum pudding. Now, when we think of pudding, we think of like Jello pudding, but this pudding is is more solid, almost more like a muffin. If you would think more of like a blueberry muffin that had sauce on it. Okay, then that's more of what plum pudding actually looks like. So he developed this plum pudding model where he said all of the positive and negative particles are just spread around, evenly distributed all through the atom, and it's still solid, but there are small pieces that make it up that can be moved. So, finally, from the atomic theory, we are able to say atoms are not solid and indivisible. There are smaller pieces which make them up. This is a picture of what you could think of it like the whole um, material is positively charged and there are enough negative corpuscles or electrons spread throughout there that make it neutral. So just everything is spread out evenly. We now can get rid of our very first atomic model, which would have been the marble model. So remember, it wasn't just Dalton's idea. Dalton brought back around Democritus's idea of this small indivisible particle known as the atom. So, why is it important, the study of the atom? Well, people didn't even believe in it. They didn't understand what electricity and light and all of this was. And Thomson was able to show them that all this electricity that's giving us this light, the lightning that we see, the static electricity that we feel, all of that is simply just these negative particles that are moving from one place to the other and that we call electrons. So this idea was not really easy for people to grasp. You know, they didn't like the idea that they were just made of pudding-like material and that they were just the same stuff as electricity. That didn't really make any sense to them. Um, so they weren't excited. They didn't believe that we were just electricity. So this atom idea was very controversial and it took a lot of time and a lot of evidence for it to become what we now know and believe makes up matter.